This is the second talk, so this is going to be an introduction to RSA. And so it might be easier to see the slides if I actually connect the HDMI cable. So the slides are not meant to be encrypted. Okay. And then okay, so it's on at least the main one. It looks like it's slowly going on different computers. Interesting, it's like a lag as to which computer goes on and when. Interesting. Okay, so out of curiosity, how many people have seen the mathematical theory behind RSA and why it works? Okay, so a good number of people have, not everybody has. So I apologize once again for probably going over things you have seen before. Okay, good, at least one person doesn't mind. It's also right after lunch, so this is the kind of time you have. Some of you I know have just had ice cream like myself. So what I want to concentrate on is how you, or at least some ideas on how you might introduce the subject to students. In particular, I know a lot of you have taken abstract algebra. I haven't taken it, I've taught it, I haven't taken it. What is the bare minimum material we need from abstract algebra in order to cover the material? So for those of you who have done a lot of group theory or want to do even more group theory, you have opportunities for side digressions with students. Okay. So the slide advancer needs to be clicked again before, okay. So RSA is named after three mathematicians who were involved, at least in the US, with the development of this idea. One of the things you have to be careful about when you talk about the history of cryptography is there is a lot of history that we do not know, or that we do not know until many years after the fact, because certain agencies have been using things for a while. So, you know, in Britain, a lot of stuff related to this was known earlier, and it's an interesting history as who knew what when, and what order were things discovered in one country versus what order were things discovered in another. We're going to concentrate on sending messages. Later on, you can talk about some interesting twists as to how do you know the message comes from the intended person. Well, it says Alice at the end. And so I like to have fun with the people who spam me and pretend to be the chair of my department, and they need me to send 8 $100 gift cards immediately for them to give as gifts. They're in a meeting right now. Can I please help them out? They go, oh, sure, happy to. And if anybody wants, I can share the email chain. Or I actually got some of these people to give me their cell phone numbers. All right. So Alice, I think by law, is always required to be the one sending the message. Bob is required to be the one receiving the message. But we don't want you to feel that this is a dictatorship. You do have freedom. The person intercepting can be either Charlie or Eve. You have a choice. But these are the canonical names that everybody always uses. And so here is the following, just the brief description of RSA as to how you implement it, and later we'll see why it works. So Bob does the following. And if I wanted to, I could have subscripts B on everything so that I could see these are the things that Bob is doing. If Alice wanted to do it, she would have subscripts of A. So Bob chooses 2 primes, P and Q. In practice, they would have at least 200 digits. Rather than spending a few slides going through and just toggling, and here you go, here you go, here you go, let's just choose 5-digit primes. So 15,217, 17,569, and Bob chooses another number D. And Bob keeps all of these secret. This is color-coded. I'll tell you in a moment where D comes from. What Bob makes public is the blue stuff, the product of the 2 primes, and some number E. And these are not random numbers D and E. These numbers satisfy the relationship that E times D is 1 modulo P minus 1, Q minus 1. Or in other words, if we subtract 1 from ED, then it is a multiple of P minus 1, Q minus 1. And as you will probably think about, oh, we've seen P minus 1, Q minus 1 before. This is coming from the Euler-Toscan function. It's how many numbers are relatively prime to N, which is just PQ. And that's why I was saying all we need is just what's going on for the product of 2 distinct primes. All right, so this is how it works. Alice chooses a message, N, M, and the message is going to be a number between 1 and big N, P times Q. And the message has to be relatively prime to N. Well, the number of numbers that divide N is extremely small. There's P and there's Q. If your number is of size, 10 to the 400, because each prime is of size 10 to the 200, all right, let's see how many messages I have to worry about accidentally 2 divided by 10 to the 400. Okay, I'm not worried. If Alice happens to choose a message that is a multiple of P or Q, she can actually crack Bob's code, and she can now read all of Bob's mail. But again, the probability of this, it's on the level of my rooting for the Yankees. It is so small, it's not going to happen. So what Bob does is he receives from Alice a message. What message? Well, she can't just send this. She wants to encrypt this. So she takes her message M, and she raises it to the eth power. And she looks at the remainder of that when she divides by n, and she sends that remainder. So she sends m to the e mod n. So for this case, it would be 121209473. And there's a lot of different ways you could have the message being encrypted. Maybe every pair of numbers is going to be a character from 0 to 99, and we can encode a lot of things that way. There's lots of different things you can do. I'm not going to talk about how you actually convert your message to a number to transmit. We just need to transmit numbers. Transmitting numbers is the same as transmitting messages. So to decrypt, all Bob does is miraculously, he raises the message he receives to the dth power and takes the remainder mod n, and when the dust settles, he gets 195632041, which is precisely the message that Alice sent him that he wanted to hear. Now imagine that a mistake happens, and we'll talk more about this later, and imagine instead of receiving 121209473, Bob receives 121209483. When Bob tries to decrypt this, he gets the message was 195632041. He gets 121141028. Only 2 numbers align, only 2 digits match. So this is very different than the alphabet codes. In the alphabet codes, if you make a mistake in 1 digit, well, the mistake stays localized. Here in RSA, if there's a mistake, essentially the entire thing is garbage. Now, I always like to do extreme cases. Is this reasonable? Is it surprising that 2 of the digits were correct? Well, if you have 2 messages that are completely independent, what do you think the probability is that a digit in the same spot in the first message is the same as the digit in the same spot in the second message? What would you guess? So we've got 2 messages. We'll assume each digit is equally likely to be chosen in each spot, and the messages are independent. So if I have a 7 in my first message in the first place, what do you think the chances that the second message has a 7 in that place? 0.1110. So you would expect about 1 out of every 10 digits to align. And if you look at what we have here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 digits. We have 2 things aligning. That's terrible data. But no, it's not, because it's such a small sample set that you would expect 1 out of 10, 0 out of 10, or 2 out of 10. That's not too surprising. If it's getting to 3 or 4 out of 10, then you can begin to be a little bit concerned. And this gives you an opportunity to talk to students about data, especially small data, and being misled. So as some of you have learned, I am a big Red Sox fan. I always take opportunities to make fun of the Yankees if it presents itself. In 2004, it was a glorious season. Not only did the Sox finally break the curse and win the World Series, but they did it by humiliating the Yankees. And so the Yankees were up 3-0 against the Red Sox. No team in baseball had ever come back down 3-0 in a best-of-7 series. No team had ever won 4 games in a row. But there were only about 24, 25 data points. So how often would you expect a team to come back down 3-0? What are your thoughts?
Very low.
Very low. Well, let's quantify very low. You know, out of how many series do you think it would take? How many situations with a team down 3-0 do you think it would be before a team comes back and wins 4 in a row?
116.
Well, it took 24. So 1 is 16. You have a 50-50 chance of winning each game. So to win 4 games in a row, it's 1/2 to the 4th, or 1 out of every 16. So you would have expected maybe 1.5 times out of 24, 25. Well, so 0's not terrible. And once the Sox do, now it's 1 out of 25 or 26. It's pretty reasonable. But of course, there's an assumption. And the assumption is that the 2 teams are equally skilled. Why might this be a bad assumption? Yeah, the other team's up 3-0. There may be a reason why you're down 3-0. The other team is better. And so it's what's the right model for what you're studying?
Did you just imply that the Yankees were better?
I said they might be better. I said they might be better. And then I have slides that I can pull up on the 2004 season and the bloody sock. So this is a wonderful example to just ask students about the reasonableness of what you're getting. And also the danger. So if one digit is mistransmitted, then the entire message is gobbledygook. And this is supposed to be motivation for the last time I talked to you about error detection and error correction. We can't afford to have even one digit wrong. Whereas if you use the standard alphabet side, if it was the best of times, it was the bluest of times. Okay, I could probably figure out what was meant in that case. If not, I have no business reading the message. All right. So here are some implementation issues. This is leaving theory and going into practice. If we actually want to use RSA, how do we find large primes? You know, I can just write, well, there's infinitely many primes, so just choose two big ones. How do we find them? How large is large enough? You know, what level of primes do we need to have a given level of security? Over time, there's these numbers called the RSA challenge numbers, where they post products and ask people, can you factor it? And there are rewards for factoring them. And certain numbers were factored a lot faster than people expected. The computers and algorithms advanced faster. And so what you think might be a good level of security may not be as good as you thought. And a lot of times, maybe you think will be secure for 5 years, but in 6 years, if somebody cracks your code and they go back and they look, they could have some important information about what you're doing. And so you have to be very concerned as to how long these things last. The next is we have to find two numbers, E and D, such that E times D is 1 mod P minus 1 Q minus 1. How do we find such numbers? The next, and probably the most difficult, is our message is going to be a 400-digit number. E is going to be a 400-digit number. So I've got to raise a 400-digit number to a 400-digit number in an efficient manner. How do we do this? The last one is the hardest one to answer. It's the security one. Eve or Charlie, here's some information. They know E for encrypt, and they know N, the product of the two primes. Can they figure out what the D is for decrypt? If they can do that, done, and they can read all the messages. Now later, if there's time in the discussion, we can talk about how Alice can sign her message digitally. And there's some great riddles you can use on this, so that when Bob gets a message, hi Bob, it's Alice, I'm in real trouble now, I need you to send me $5,000 cash fast, thanks, love you. Does Bob trust this message? Oh, I forgot to say, she signs it, love Alice. And Bob, oh, it's signed love Alice, so it must be a valid message. So what can Alice do to convince Bob that it really is her? And this is absolutely essential. Otherwise, if we want to do communication in the 21st century, we would have to go to each site first in person and introduce ourselves. Hi, Amazon, I'm Steve. I'd like to buy products from you. Let's exchange things so that you know I am I. And then when my bank has to pay money, they will know it's okay. So you want to be able to exchange secrets without physically meeting. We talked a little bit about the one-time pad and how unbreakable that is if used correctly. But one of the challenges is it requires the people to be present to exchange the one-time pad. How do you share a secret in a crowded room where people can be listening to your conversations? Okay, so I want to talk a little bit about Fermat's little theorem. So there's Fermat's little theorem and there's Fermat's last theorem. They both have the same 3 letters. You normally write little with a lowercase l, so it's F lowercase lt versus F uppercase lt for Fermat's last theorem. I will state the theorem maybe in full generality, but I will concentrate on the proofs just in what I need for RSA. You're going with the theme of what is the bare minimum we need to do. So as we remember from earlier, phi of n is the number of integers from 1 to n that are relatively prime to n. We've decided that we're going to look only at primes and products of distinct primes, and we get phi of p is p minus 1, and phi of pq is p minus 1 times q minus 1. Okay, great. Now, we don't need it, but as I've remarked, a really good exercise is to prove the function is completely multiplicative. There's a lot of group theory lurking in the background, and we'll just advance and ignore it. All right, so the little theorem is imagine A is relatively prime to n. That if you take any such number A and raise it to the phi of n, you get 1 mod n. So whenever you see a theorem, you want to explore, well, what would happen if I removed some of the conditions? Well, if A has a multiple has a factor in common with n, say they're both multiples of 3, then A to any power is also going to be a multiple of 3. And there's no way that this could then be 1 mod n, because this is a multiple of 3, n is a multiple of 3, so when I subtract it from 1, this would be negative 1 mod. Okay, So it's clear that I have to have A and N relatively prime. The special cases for us is if we take N to be a prime, we get A to the P minus 1 is 1. And if N is the product of two distinct primes, we get A to the P minus 1 Q minus 1 is 1 mod PQ. So if you're giving this to students, you don't give them Fermat's little theorem. You can have them do some explorations and see if they can figure out the pattern. Is there anything interesting? You know, what power, if your N is a prime, do you start to see interesting things happen? And you might eventually notice, I keep getting 1 at P minus 1. And it can highlight an idea of what you might want to try to prove. So we're going to prove these two cases. The first proof is going to be in the case when N is a prime. And this proof can be tweaked with very little effort to work for all N, but I do not want to do that tweak. So we'll let N be P. We'll choose a number A such that the greatest common divisor of A and P is 1, so they're relatively prime. So consider the numbers 1, 2, all the way up to P minus 1. And consider the numbers A, 2A, 3A, 4A, all the way up to P minus 1A. So what I've basically done is I've taken every element in my first list and I've multiplied by A. And so the key observation is that these two sets, if I look at them modulo P, they're precisely the same. They're just the numbers 1 to P minus 1. The second set is just rearranged. So it's clear that 1, 2, all the way up to P minus 1 is just the numbers 1, 2, all the way up to P minus 1. That's not a big deal. The second one requires a slight amount of additional work. So let's say I times A equals J times A mod P. So let's say that two different multiples on the right go to the same number. Well, I can then subtract and I get I minus J times A is 0 mod P. So that means P divides the product. It is amazingly a non-trivial theorem to prove if a prime divides a product, then it has to divide at least one of the two factors. This is one of the things that is like, of course, but it actually requires a little bit of mathematical sophistication to prove this. And you have the opportunity when you're teaching this to you want to actually go into that. Do you want to say, here's an article you can read on that, or come on, it's obvious, let's move on. And maybe show people some other things that seemed obvious that were false, like Russell's paradox, to just warn people that we're not proving this, but you got to be careful. Well, we'll just assume that if a prime divides a product, it has to divide at least one of the two terms. Since A is relatively prime to P, that means P has to divide I minus J. And since I and J range from 1 to P minus 1, the only way that that difference can be a multiple of P is if I equals J. So that proves we can't have two different numbers here having the same residue. And now this goes back to that first idea we saw when we were looking at, I want to encrypt letters. I want two letters to never go to the same letter, and I want every letter to be hit. Because we have a finite set, we actually don't need to specify both of these conditions. Because now everything goes to a different number, and there's only finite many things, everything is hit once and only once. And so now we just multiply both sides. So if we multiply 1 to P minus 1, we get P minus 1 factorial. And if we multiply A, 2A, 3A, all the way up to P minus 1A, we get P minus 1 factorial again, times A to the P minus 1. And now the idea is, well, since these are equal mod P, P doesn't divide P minus 1 factorial, so I can just remove the P minus 1 factorial from both sides. And we're left with A to the P minus 1 is 1 mod P. And that's the proof. Now, the general case, what's nice in this case is we know the numbers are 1 to P minus 1. If I chose a number N, which is not a prime, well, then I have phi of N numbers, I could call it X1 to X phi of N. I multiply each one of them by A's. And you can try to do the proof in a little bit more generality. You would have a little bit of symbols to work with. It's not too bad. The same idea still works. I want to avoid going to something like this and just focus on the cases we need. So I love backdoor proofs. So let's let N equal PQ, and let's let the greatest common divisor of A and PQ be 1. So again, we're going to choose a number A that's relatively prime to PQ. I'm going to try to prove that A raised to the P minus 1 Q minus 1 is equal to 1 mod PQ. So the first is I'm going to apply Fermat's little theorem with not A, but A to the Q minus 1. And my prime will be P. So if A is relatively prime to P, so is any power of A. So I get A to the Q minus 1 raised to the P minus 1 is 1 mod P. That's just Fermat's little theorem applied to A to the Q minus 1 and P. Now I'll apply Fermat's little theorem again to a to the p minus 1 and the prime q. And I'll get a to the p minus 1 q minus 1 is equal to 1 mod q. Well, these numbers are the same. When you have exponents, it doesn't matter which order you multiply in. So in both of them, I get a to the quantity I want, p minus 1 q minus 1. The first one tells me it's 1 mod p. The second one tells me it's 1 mod q. So if it has remainder 1 when you divide by p, and it has remainder 1 when you divide by q, what's its remainder when you divide by pq? It would also be 1. And so that's the last thing you have to show. So it's got to be 1, and here's why. We know it's 1 mod p, so I have to be able to write it 1 plus some multiple of p. Let's say 1 plus alpha p. It's also 1 when I divide by q, so it's got to be of the form 1 plus beta q. All right, so I can now solve for alpha and beta. And so when I subtract 1 from both sides, I get alpha p is beta q. Since p doesn't divide q, they're distinct primes, p must divide beta. Since q doesn't divide p, they're distinct primes, q must divide alpha. So alpha is a multiple of q, beta is a multiple of p. So a to the p minus 1, q minus 1 is 1 plus a multiple of q times p, or 1 plus a multiple of p times q. That's what I needed to prove. So we can actually get the version of Fermat's little theorem that we need without doing the general case, by just cleverly using the case of Fermat's little theorem for a prime. And I really like this idea of just trying to see just how far can you push something. Okay, any questions on this part up to now?
Fermat was born in the 17th century. Euler in his work is in mid-18th century.
Right.
Fermat cannot use Euler torsion function. What he used? What language he used?
That's a good question. That's a good question. I'm not sure what language he used, and I'm not sure if he wrote it down in the general case or if Fermat only did a to the p minus 1. That's a really good question, because you're absolutely right that he would not use the language of the torsion function. And sometimes it's interesting as to what name do theorems go by. And so sometimes the special case becomes the name of the general, but it was not proven in that generality initially. So that you're right, that's something that's worth looking up. There is a nice consequence of Fermat's little theorem, is that you can use this for primality testing. So imagine that a and n are relatively prime, and we calculate a to the n minus 1, and it is not 1 mod n. Well, we know that it has to be 1 mod n if n is prime. So this is a way to tell that n can't be prime. This seems absurd. You're basically able to tell a number's composite without giving a factor. I just know it's not prime. Huh? Okay. Now, if it equals 1, then it might be prime. So as a nice exercise, you can take certain composite numbers like 6 and go through and calculate this, and you can find out that 6 is composite without knowing a factor of 6. Now again, 6 is not a particularly challenging number. I'm sure, based on our ability to use the affine encryption scheme, that we could factor 6 very quickly if we had to as a group. But it's nice to be able to know that you could prove something like that as composite without giving a factor. So if we want to use this, we need to be able to take high powers of numbers very, very fast. If n is going to have 200 or 400 digits, how do I calculate a to the n minus 1? Yes, theoretically, I look at a to the n minus 1, but if I can't compute it quickly, this is useless. It suggests candidates for primes. So factorization, we don't know an easy way to do it. There might be, and if there's quantum computers, factorization becomes much, much easier. But right now, with the computers we have, we do not know any algorithms to quickly factor a number. What's nice about Fermat's little theorem is it will allow us to quickly check if some numbers are good candidates for prime. And if a number passes this test for a lot of different values of a, then it's likely to be a prime. If we want to be absolutely sure that it's a prime, there are some slightly slower algorithms we can use that will guarantee that it's prime. Unconditional, doesn't depend on anything. It will just run in polynomial time based on the number of digits of the number. So if we have to be sure, we can. This tells us how to allocate our time. It tells us which numbers is it worth checking carefully. If you can quickly eliminate some things, Great, we don't have to bother checking them. Now, it turns out that there can be infinitely many numbers that satisfy this condition. A to the n minus 1 is 1 mod n without being prime. And these are called Carmichael numbers. And the first few are 581, 1105, etc. There's a wonderful website called the Online Encyclopedia of Integer Sequences, the OEIS. And if you have any string of numbers, if you plug it into that sequence, it will generate lists of sequences that it knows that has those as a start. And it will often give you links to formulas about those numbers, to papers about them. Absolutely wonderful site. So there's a lot that we can do with Fermat's little theorem. And it can help us with that question of finding the primes. Okay, so now it's time to do fast multiplication. So out of curiosity, how many people here have seen Horner's algorithm? Okay, good, some but not that many. This is one of my favorite algorithms. And the reason I love this so much is it allows you to talk to students about how something you've been doing all your life, you may not be doing it as efficiently as possible. And that there are opportunities for savings. For a lot of my students, I tell them, you don't have to do things the best. You just have to do things better than is being done to be useful and to make a contribution. And that's a much lower bar that I feel I can hit with great ease. And so Horner's algorithm is all about trying to find better ways of multiplying or evaluating numbers. So imagine I give you the beautiful function f of x is 3x to the 5th minus 8x to the 4th plus 7x cubed plus 6x squared minus 9x plus 2, and I want to evaluate it at a value of x. Well, you should imagine that these numbers x are very large. And when I'm multiplying numbers or adding numbers, there's a different cost. If I have two 200-digit numbers, let's say we write the numbers in base 2. How many operations is it to add to 200-digit numbers, roughly? So if I want to add 200-digit numbers together, how many operations? So I write one number, then I write the next.
We're using standard algorithm.
Well, so maybe the numbers are, and the next one is, and I want to add these numbers. So how many operations is it to add these numbers? Well, 200, or maybe there's carrying, so maybe it's twice that. But the cost is going to be proportional to the length of the number. If it was 500, it would be some nice multiple of 500. If it was D digits, it would be a cost of D. If I want to multiply now, well, this number has to multiply all the ones here, this has to multiply all the ones there, so its multiplication is going to be on the order of D squared. So if you have a 200-digit number, the cost of multiplying two such numbers is so much larger than the cost of adding them. For the purposes of our analysis, we'll basically say addition is free. We don't really worry about the cost of addition because it's dominated so much. There has been a slight change at lunch. Midge was kind enough to inform me that Dymax has received a windfall of donations, and everybody will be getting $1 million stipend for coming today. Oh, yeah, I'm looking at Midge. Oh, Midge reminded me that there was an error. It's actually $55 less than that. Okay, nobody should be upset about losing the $55. If you are, we have bigger issues to talk about than mathematics. The size is so small, it's immaterial. Okay? That's how you should look at the addition versus the multiplication here. Okay. So when I want to figure out what is the cost of multiplying, to calculate 3x to the 5th, x times x is x squared, times x is x cubed, times x is x to the 4th, times x is x to the 5th, times 3 is 3x to the 5th. So this costs 5 multiplications to get 3x to the 5th, 4 multiplications to get 8x to the 4th, 3 to get 7x cubed, and so on. So the number of multiplications is 5 plus 4 plus 3 plus 2 plus 1 plus 0, or 15. And so these are going to be the triangle numbers, and these numbers will show up again later tomorrow. The triangle number of degree D is going from 0 all the way up to D. It's going to be D plus 1 over 2. There's lots of ways to prove this. You can do it by induction. You can also write the numbers in reverse order. 5 plus 0 is 5. 4 plus 1 is 5. 3 plus 2 is 5. So you would get 5, 6 times. So you've double counted, so you would divide by 2. So this tells us that the cost of just brute force evaluation is going to be of size roughly d squared over 2. And so if you have huge numbers, this is going to be tremendously bad. And this is just the proof of how to add them. Okay, so here is Horner's beautiful algorithm. It converts an algorithm of order d squared to an algorithm of order d. And what you do is the following. Well, look, it's kind of stupid to compute x to the 5th and x to the 4th separately. Because to get to x to the 5th, I go through x to the 4th. And to get to x to the 4th, I go through x cubed. So let's rearrange the computations in a more clever way. So hopefully all the different colors are showing up. So we get 3x minus 8 times x plus 7 times x plus 6 times x minus 9 times x plus 2. So if you take the 3x, it hits 1, 2, 3, 4 more x's, that's going to give you a 3x to the 5th. You have the negative 8, it hits x, 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 x. It'll give you a negative 8, x to the 4th, et cetera, et cetera, et cetera. And now when you look at the cost, well, I have 1 multiplication from 3x, and then 2 from this x, 3 from this x, 4 from that x, 5 from that x. So multiplication goes from d squared over 2 to just order d. Much, much cheaper. So an order d algorithm is not bad, unless d is big. So if d is of size 10 to the 400, yes, 10 to the 400 is much better than 1/2 of 10 to the 400 squared. But 10 to the 400 is so huge that it is impractical to use something like this. I do not know a better algorithm than Horner if I have to look at a general polynomial. But maybe we don't have to look at a general polynomial. So one of the challenges is if you are trying to find something that works for everything, well, there's so many different things you have to handle. It'll work for everything, but it's almost surely not going to be optimal for a lot of things. So maybe we could look at a very special polynomial, which might be easier to evaluate quickly. So this is a polynomial of degree 5. It takes a little bit of work to evaluate it. Can anybody give me a simpler polynomial of degree 5 to evaluate? Yeah, x to the 5th, right? Or polynomial of degree g, just do x to the d. So maybe if we take a pure polynomial like that, we can do a lot better. And if you think back to what we saw when we looked at how RSA is implemented, we're going to take a message and raise it to a huge power. So that's all we need to do is raise something to just a pure power. So what we're going to do is we're going to look at f of x is x to the n. So I always choose the same value, and I always choose n equals 100, because this way I always remember what the binary expansion is. Although it's nice being in a room like this where there's actually cameras in the back. I feel like I have a teleprompter. And I can just see it's supposed to be 100 is 64 plus 32 plus 4. Or writing it in base 2, the subscript 2 means base 2, it's 1100100. So if you were to calculate x to the 100 naively, there would be 99 multiplications. If n was of size 10 to the 400, it would be 10 to the 400 minus 1. The minus 1 doesn't matter. It's like that $55. Impractical. But here's how to do it efficiently. So x times x is x squared times x squared is x to the 4th, x to the 4th times x to the 4th is x to the 8th, et cetera, et cetera, et cetera, all the way down to x to the 32 times x to the 32 is x to the 64. And now let's look at our number x to the 64. We need 64 as one of the factors in x to the n. So what we can do is we will write x to the 100 as x to the 64 plus 32 plus 4. So that's x to the 64 times x to the 32 times x to the 4. So if I can just calculate these three numbers and multiply them, I can get x to the 100. I don't know why it's not. Okay, so I start off with, I want x to the 64. I want to multiply it by x to the, oops, wrong direction. I want to multiply it by x to the 32, so I include that. I don't need x to the 16. I multiply by x to, I don't need x to the 8, I multiply x to the 4. How many multiplications does it cost me? 1, 2, 3, 4, 5, 6. It cost me 6 multiplications to get to x to the 64, 7 multiplications to get x to the 32, and then 8 multiplications to include the x to the 4. 8 multiplications. And again, the way you should look at this is it's not 8 versus 99. I should look at it, if it was degree D, Horner's algorithm would take D steps. Well, Horner's algorithm is stupid. It's a technical term. When you are applying it to x to the 100. Because if we have no multiplications and no subtractions here, we just have x times x times x times x times x. Horner's algorithm reduces to just brute force evaluation. There's no savings in using Horner's algorithm if we just have x to the 100. But when we do it like this, anybody know how many multiplications this really costs us, worst case? So I want it as a function of the number of digits. So, I have x to the 100, or more generally, I have x to the d. So the first thing is we have to figure out what's the highest power we have to go down to. So we have to go down to 64. So we will need the highest power of 2 that's less than d. So we need to solve, 2 to the, I'll call it r is less than equal to d, but 2 to the r plus 1 is greater than d. Because when I'm writing my number d, when I'm writing my exponent in base 2, I need to figure out what's the highest power of 2 I can take and still be less than equal to my number. I'm clearly not going to expand using a number greater than d. So if I want 2 to the r less than equal to d, this means that r is less than equal to the log base 2 of d. And now we know that the highest power we need to go to okay. The highest power we need to go to is going to be essentially like the log of d base 2, but then we might have to multiply everything back up. So it might take us log of d multiplications to go all the way down, and we might have to multiply everything again, so there could be another log d. That's fine, that's just log d plus log d. That's just twice log d. Twice log d is doable. If d is of size 10 to the 400, which is what we need in applications, we talked about how if every subatomic particle is a universe of where every particle there is a universe of supercomputers since the dawn of time, we can't make a dent in the problem. In this case, the number of computations we need to do is not 10 to the 400, but twice the log of 10 to the 400 base 2. All right, that's going to be 800 times the log of 10 base 2. Can somebody give me an upper bound for the log of 10 base 2? It's at most 4. So 800 times 4 is 3,200. Doing 3,200 operations is not bad at all. And when we're doing the multiplications, we constantly do the multiplications modulo n so the numbers don't get too large. So we don't have to worry about overflows. So this becomes a very doable computation. You only need a computer to do things less than 4,000 times. That's not bad. And so I have the Mathematica code. If anybody does Mathematica and wants to see that, I'm happy to include that in the stuff that I'll show. I'll post that on the webpage later. So if we look at a very special polynomial, then there is the opportunity of having a better algorithm. And this is a great concept. We're no longer trying to do the best for everything at once. We're trying to say, can we do better for this one particular case? And the answer is yes. Okay. Any questions up to here? So we're going to now pivot to the next part.
Could you please explain again why you take 100 equal to 64, 32, 4? Sorry, I just missed that part.
Sure. So what I'm doing is I'm looking at the base 2 expansion of 100. And more generally, if I gave you any power n, I would write n as its base 2 expansion. And so now what I do is I need 100. Actually, so 100, x to the 100 is the same as x to the 64 plus 32 plus 4. So it's x to the 64 times x to the 32 times x to the 4. So if I can just compute these perfect powers of 2, then I can get x to the 100 by multiplying them together. And that's the power of doing things in base 2. Okay, so now we're switching to the next part of the RSA lecture. So Fermat's little theorem allowed us to find candidate primes very quickly, and then there were methods that we can move from candidate to actual primes. And we got to use the torsion function again and see a little bit of the group theory lurking in the background. We then just did Horner's algorithm to show that we can do things better, but Horner's algorithm wasn't good enough. We then did fast multiplication. So these huge exponentiation problems aren't going to be bad. But there's one thing that's left. We have to find two numbers E and D such that E times D is 1 mod P minus 1 Q minus 1. So two of my colleagues, Colin Adams and Tom Garrity, have a debate as to which is better, the Euclidean algorithm or the trefoil knot. I have heard it is a brilliant, witty piece of mathematics. I've heard students love it. I've never listened to it because there is no need to listen to it. It's clear the Euclidean algorithm is better. I don't understand how my colleague Colin Adams was able to talk about the trefoil knot as long as he did relative to the Euclidean algorithm. The Euclidean algorithm is one of the ultimate algorithms in mathematics. It is easy to encode, and it is fast and efficient, and it gives you a tremendous wealth of information. When I was a postdoc at Brown, there was a donor who really liked Thoreau and donated a lot of Thoreau's stuff to the libraries at Brown. And so I actually got to look at some of the donations, including his algebra book from Harvard. And so I actually got to see his math scribbles where he was actually writing down the Euclidean algorithm and doing this to compute some numbers. This is what we need to do the last ingredient. So the input is going to be two numbers, x and y. We'll assume y is greater than x. And the goal is to find the greatest common divisor of x and y. Actually, we want to do a little bit more than that. We want more than just the greatest common divisor. We want to find numbers a and b such that a times x plus b times y is the greatest common divisor of x and y. And it turns out it's going to be very valuable to find such a and b. There's a lot we can do with this. And there's a lot of ways to go about this. There's some non-constructive proofs that tell you a and b exist. But for a lot of things in life, it's not enough to have a non-constructive proof. There's an election that's going to be happening in this country in a couple of months. Imagine you are hired by one of the campaigns and you report back, good news, I have found that there is a strategy that will allow you to win the primary and win the general election. That's wonderful, what do I do? Well, it's a theoretical proof. You can imagine your ability to gain a consulting gig after that. In the real world, it's not enough to prove that something can be done. You need to give a procedure that will allow you to do it, presumably in real time. You don't want things to come out, okay, in 2024, here's what you should have done. Although a lot of pundits seem to make a lot of money. All right, so let's let R naught be Y and R1 be X. And the reason is, this way we can have a unified notation. If we have X and Y, those are special letters. This way I'm going to have a chain. I'm going to keep constructing new letters in the sequence. So we'll start with R0, R1, coming next, R2. So I write my number R0 as a multiple of R1 and a remainder. So Q1 R1 plus R2. And so this is just a simple division algorithm. I throw away as many copies of R1 as I can, and then at the end of the day, R2 has to be an integer between 0 and strictly less than R1. If the remainder happened to be R1, well, I could have increased Q1 by 1. If it's greater than R1, I could have also increased Q1 by 1. So I can keep doing this. I can keep throwing away multiples of R1 until I'm left with an R2 that is strictly less than R1. And now we just keep repeating, lather, rinse, repeat. I now write R1 as Q2 R2 plus R3, where the remainder R3 is strictly less than R2. Is it possible for this process to continue indefinitely? No. Can you give me an upper bound on how long it could take to finish? Yeah, basically R1. Worst case scenario, every time we apply this, it goes down by 1. Well, if your number's of size 10 to the 400, if the runtime is of size 10 to the 400, it's useless. This is the worst case of the worst case scenarios, where at every moment in life, the worst thing that could happen to you happens to you, and it continues to happen to you. It turns out that life can't be this bad mathematically this long. And there's a wonderful result, it's a nice homework problem, to show that every 2 steps, you have to decrease by at least a factor of 2. So it's possible to have a short drop. I go from R1 to R1 minus 1. Crap, I only decreased by 1. Well, imagine R2 is R1 minus 1. Ooh, I want to write R1 as a multiple of R1 minus 1 with a remainder. Well, it's going to be a multiple of 1, and then the remainder will just be 1, and it will drop down tremendously. So if R2 is very close to R1, then R3 is going to be very, very small, and you win. If R2 is far away from R1, you win. So you basically just have to analyze the two different extremes. You can't constantly be bad. And it turns out that the Euclidean algorithm, very similar to fast multiplication, runs in logarithmic time. So the time is going to be like twice the log of x or something like that. So it will run very rapidly. So we keep doing this and we continue until we get to r to the n is qn plus 1, rn plus 1 plus rn plus 2. And in the end of the day, rn plus 2 is either 0 or 1. If it's 1 and you want it to be 0, you just run it one more time. And the important thing to note is that as we do this, we preserve what the greatest common divisor is. And so the greatest common divisor of R0 and R1, well, imagine I have something that divides both R0 and R1. I can write R2 as R0 minus Q1 R1. So if I divide both R0 and R1, I divide R2. Conversely, if I divide R1 and R2, I'm going to divide R0. So as a nice exercise, you prove that the greatest common divisor is preserved as you march down the sequence. And so if we end with a 1, then the greatest common divisor was a 1. If it's a 0, you then just look at the previous level. So there's a limit to how many technical details you want to go through. I was told to have some homework problems. So here's a good homework problem. Take some numbers, run it all the way down, and then run it backwards and find out what are the a and b such that ax plus by is the GCD of xy. So once you have all this, with a little bit of bookkeeping, you can actually run it upstairs, run it backwards, and get those values. And then we'll see in a moment why we want these numbers. All right, so implementing RSA. So first we choose, oh yes.
So you mentioned the other algorithms. So your two colleagues were debating if the Euclidean or the, what was the other one?
The trefoil knot. So it's not even worth mentioning. You should just say the Euclidean algorithm or something else. Like with like hands going down like that.
So what is it about?
It's just a humorous mathematical debate where they're both talking about
the other algorithm.
Oh, it's not even an algorithm. It's just a knot it's just a knot. You're just like tying a piece of string.
No,
yeah. They also have a debate on which is better, e or pi, which is better, the derivative or the integral.
Okay.
So they have a whole series of these. And some of the other ones, Professor Adams has reasonable positions. E versus pi, I can see some arguments. Derivative versus integral, I can see some arguments. But the trefoil knot versus the Euclidean algorithm, I mean, he debates it beautifully, and he often wins the argument, which is more of an indication of the lack of mathematical maturity of the audiences. But the Euclidean algorithm, it's just tremendous what it allows you to do. So, okay, you can use the trefoil knot to tie things down.
Yeah.
But, all right, so let's actually implement RSA and see what we need to do to use it. So the first is we want to choose large primes P and Q. We can do that using Fermat's little theorem. It gives us candidates very easily. And I'm not going to prove this now, but if you count the numbers up to x and ask how many numbers are prime, so let pi of x equal the number of integers at most x which are prime. The prime number theorem says that pi of x is approximately x divided by the log of x. What this tells you is there's a huge number of primes. Now, the density of primes goes to 0. So the density of primes up to x is pi of x divided by x, which is approximately 1 over log x, which goes to 0 as x goes to infinity. So the probability that you choose a number that's prime, it's going to be very small. But on average, how far do you have to walk from a number before you get to the next prime? you only have to walk on average about log of x steps. So even if x is of size 10 to the 400, there's not that many numbers you need to check with high probability before you find the next prime. Okay? There are no nice formulas for finding primes, but we can check the spaces without too much trouble. So we can use Fermat's little theorem to get candidates. If you want to be really safe, you can then use a high-level method to be sure that it's prime, although you're probably safe just assuming it's prime. Now, we use the Euclidean algorithm as follows. So we had to find numbers E and D such that E times D was 1 mod phi q. So let's choose a number E randomly as our candidate. So we choose an E and we hope it works. We hope that there is a D such that E times D is 1 mod phi q. Well, let's apply the Euclidean algorithm. Let's take X to be E, and let's take Y to be P minus 1, Q minus 1. If E and Y are relatively prime, then when we apply the Euclidean algorithm, we'll get a choice of A and B such that AX plus BY is 1. And then we win. So now what we would have in that case is A times E plus B times P minus 1 Q minus 1 equals 1. So this is what happens if the number E turned out to be relatively prime to P minus 1 and Q minus 1. I'm searching for a number D such that E times D is 1 mod PQ. I can rewrite this as A times E is equal to 1 minus B times P minus 1 Q minus 1, or A times E is 1 mod P minus 1, Q minus 1. So if E and P minus 1, Q minus 1 are relatively prime, then the A and the B I get from the Euclidean algorithm, actually I only care about the A, that will be my D. So now take D equals A. And then you can ask, how likely is it for E to have a common factor with P minus 1 and Q minus 1? Well, if P minus 1 and Q minus 1 were primes, it would be very unlikely. So your trouble depends on how many prime factors P minus 1 and Q minus 1 have. They're not going to have that many prime factors. It's going to be very hard to have a collision. If you have a collision, just try again. Now what you might do is you might try maybe a special type of prime. So let's consider large primes. Okay, so large primes are at least 5. Small primes like 2 and 3 can cause some issues. Can P minus 1 ever be prime if your prime is large? No. That's why we have to say large, because for small primes like 3, P minus 1 can be prime. What must P minus 1 be divisible by? 2. So we say you have a Sophie Germain prime. I don't think there's an E at the end of her name, is that correct? If P minus 1 over 2 and P are both prime. And so basically for the Sophie Germain primes, we know P minus 1 can't be prime because it's a multiple of 2. But if the only factor you have is 2 and P minus 1 over 2, doesn't have that many factors, and it turns out these numbers have some remarkable properties. So she was able to prove, I believe, Fermat's last theorem held if the exponent was a Sophie Germain prime. And for Fermat's last theorem, it's enough to study what's going on just for the prime exponents, and you can get the other ones by playing some nice fun games. So there's a lot of nice digressions you can take with something like this. Since this is being recorded, if any of you are interested, you can always email me, but that's why I'm trying to just say a few things like this. So maybe we should take a Sophie Germain prime pair for P and another Sophie Germain prime for Q. Or maybe this is the worst thing possible to do because these are no longer generic primes. And maybe people who are trying to attack could somehow exploit the fact that we have chosen a very special prime. You've got to be very careful. Just because you don't see a way to exploit something doesn't mean someone else does. So my feeling is this would either give you the greatest possible security or the worst. Probably not the middle. But we can use the Euclidean algorithm to find the E and the D we need. And now we use fast multiplication to compute M to the E very efficiently. So this is basically what I wanted to say for RSA. Before we move on to this next part, I thought we would just stop and see if there are any questions. There's a tremendous amount to digest. This is some of the most influential mathematics in the 20th century. It allows people to communicate efficiently. It allows them to transmit messages with unbelievable amounts of security. So there is a tremendous amount of reading you can do about the Enigma, which was the code the Germans used in World War II, where they believed that the number of combinations was so astronomically large, there was no way the Allies could crack it. Now, if the Germans had used the Enigma properly, I believe they would have been correct that it could not have been cracked. But they made some very small mistakes. And those small mistakes were the entrances the Allied cryptographers needed to get in and crack the code. So the idea here is to try to take an object that is so complicated that if you don't know a special extra bit of information, a special backdoor, you can't do the math. If I know what the primes P and Q are, let's go back to the description of RSA. So if I know what P and Q are, I know what P minus 1 and Q minus 1 is. So if I know the E for encrypt, I can figure out the D. So it's not hard for somebody to figure out D if they happen to know the 2 primes and the E. The question is there any way to easily figure out what the D for decrypt is if you only know N, if you only know the product of the primes and D? To date, no person has publicly stated that they know an easy way to do this. There may be an easy way to do this, but it has not been stated. So there is a tremendous amount of stuff going on here. The goal is to try to show you and inspire you to read that book. So Midge and I can get another, I think, $1.50 to split. But to show you, what's out there. What do you need to actually do this? We're doing this all in less than 50 minutes. You spread this out over several weeks. Here you do a little unit on Fermat's little theorem. Here's what you need to build up. Here's some side excursions you can do. Here's what you need for fast multiplication. And I know at least one person here is teaching linear algebra. There's a lot you can do from Horner's algorithm. The next thing I would go to is the Strassen algorithm. So I'll just write the name here. Out of curiosity, how many people have seen the Strassen algorithm? Okay, much, much less. So if I give you 2 n by n matrices, so n by n A and another n by n matrix B, and I want to let C equal A times B, the question is, how many operations does it take to compute this new matrix? Well, the matrix has n squared entries. So C has n squared entries. And for each entry, I take a row of A and a column of B, and I take the dot product. That's going to be n multiplications. Each costs n multiplications. I'm sorry? No, we don't care about additions. Additions are cheap. So addition is so cheap, yeah. We're not even going to notice it on the bill. Each costs n multiplications, so the total cost is n cubed multiplications. So it's growing cubically. It turns out that there is a more efficient way to multiply matrices. It starts by looking at 2 by 2 matrices, and then it takes a general n by n matrix and breaks it up into 2 by 2 blocks. So this is why for a lot of applications, you want the size of your object to be a power of 2. It just means it's very easy to implement these algorithms. And the cost for Strassen, and Strassen is no longer the best, but it's easy to implement, is n to the log of 2 base 7. So what can you tell me about the number log of 2 base 7? It's less than 3. So really, I shouldn't say that this is n cubed multiplications. I should say it's n to the log base 2 of 8 multiplications. And so the savings is replacing the 8 with a 7. This doesn't look like this is worth being excited about. It is worth being excited about. It is a power savings. And if your matrix is 10,000 by 10,000 or 100,000 by 100,000, a small power savings is tremendous. And this is one of the greatest applications that you can have. And it will tremendously cut down the runtime. And what happens is you introduce a bunch of subsidiary auxiliary quantities to compute. And you can get all of the entries of a 2-by-2 product with just doing 7 multiplications and a few more additions. So there is a cost with some extra additions, but addition is so cheap, we don't worry about those costs. As another item that you can go with for Horner's algorithm.
Wait.
Yes.
A second, Steve.
Okay.
So what is Strauss's algorithm? Simply how you multiply the two matrices?
Is how you multiply the two matrices. And so if you just go to Wikipedia, you can just Google Strauss and it will tell you how to construct the matrix, a 2-by-2 product. And you will introduce 7 auxiliary quantities, or maybe 8 auxiliary quantities, but using 7 multiplications. But you get these auxiliary quantities using just a small number of multiplications. And because you've saved 1 multiplication, it doesn't seem like this is that big of a deal. And yes, if I'm comparing 7 multiplications to 8, it's not worth being excited about. But it scales up. And that's the whole point, is that small little extra efficiency becomes tremendously large. So this is another avenue to go in lectures like this as to what material you're learning. The last one to just briefly mention is fractals. And so if you want to evaluate fractals, what you typically have is you have a function, you keep iterating it again and again and again. That function is often a polynomial. If you can evaluate the polynomial a little bit faster, you can do much better zooms. So if you go online to YouTube, if you type in either the Mandelbrot set, or if you type in the Newton fractal, you will get tremendously beautiful pictures with phenomenal zooms. And you need to be able to do any little bit possible to save your runtime and your computations if you want to get down deep. So I know there's a lot of material here. The goal was to have the high-level stuff, all the content here, so there's plenty of time for the discussion. The last lecture is actually going a little bit backwards and not doing any high-level mathematics. There's, I don't think, any functions or anything like that, any large evaluations like this. It's all about finding efficient ways to look at things.
Are there problems that you can give REU students based on just what you've done in the last half hour?
I am very hesitant to give an REU student any problem related to elementary cryptography just because of all the stuff that's out there. And I'm just afraid, if all that I'm looking for is for them to have a research experience and it doesn't have to be new work, then yes, you can generate stuff like this where they're discovering it for themselves. But I'm always afraid, is this just already known somewhere in the literature? And is it interesting? If you can't use it in an efficient real-world manner, it doesn't really matter. For the last lecture, the one on error detection, error correction, there are some problems I'm giving some high school students this summer and maybe some college students to try to see, this is inspired by some conversations Jim and I had for one of the modules, can you find other efficient ways of detecting and correcting errors? And these almost surely will not beat what exists. But that's fine. The goal is not to come up with something that we can implement. There are major corporations and national institutes of very smart people with comfortable offices devoted exclusively to trying to find stuff like this. I'm not going to have a couple of high school and undergraduates rumble with them. Doesn't mean you can't win. So I mentioned that there are algorithms that are deterministic to tell you if a number is prime that run in polynomial time in the number of digits. The best algorithm we know, and the first one to prove that you can do it in polynomial time, was done by an Indian computer scientist and his 2 undergraduates. And they completely surprised the scientific community when they came up with this. They beat everybody. So it is possible. That's the only example I know of.
Steve, during your classes, do you only consider theoretical concepts and very not simple, but not heavy exercises like you showed with?
It depends. It depends on the students.
How you use computer and the methods.
So a lot of it depends on the background of the students. So in the fall, I'm going to be teaching operations research again, which is one of my favorite classes to teach. And so I wrote a book on that with an extremely heavy number theory accent. So it's probably the only number theory cryptography book you will see. And so I don't prove all the algorithms in terms of the runtimes, perfectly, but I give some analogies from number theory to give students a sense. And sometimes I have students who have never programmed before and they just want to do theory. Other times I have students from computer science and they want to do implementations. So I have them do schedules, and a lot of times they do consulting jobs for local companies. One of them actually did a solution for a judging for an annual tournament where they had all these conditions on, we only have a finite set of judges, we don't always know how many judges are going to show up, how do we schedule them given that these judges can't work together more than this many times, blah, 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 blah. One of my favorites, I've got to be careful how I phrase this because this is being recorded, is one of the early successes of linear programming is something called the diet problem. So imagine you're a dictator and all you care about is keeping your population alive just enough to do what you want. So you want the cheapest possible diet for them so that they don't die. And so you have a bunch of different substances with different nutritional values, and you have certain minimum daily allowances. What is the cheapest possible diet you can have? And so there were some very amusing stories the very first time George Danzig ran this, where they didn't realize some of the stuff, and so you're drinking these incredible vats of horrible things. So my students who were doing this as one of their research projects a few years ago noticed that one of the local supermarkets has the service where you can order food online. And because you can order the food online, you have to be able to access certain information about the food. They had the ability to write certain programs to go through various food products and pull out information about the food products. And so they actually went through the supermarket and got the actual information about all the products, and they looked at what the US recommended or the daily minimum requirements, and they found what the cheapest diet possible was. And then they went one step further. They then went one step further. After finding what the cheapest diet was, and they were presenting this to their class, they then opened a box and put out in front of me a plate of the cheapest possible way to stay alive. So I have a picture of that sumptuous meal that they made for me. There's a certain type of bean that is extremely good and was useful for a lot of the stuff they needed. There were various liquids that were poured on it. And, I gave them tremendous points, not just for the presentation, but for the fact that they actually wrote the computer code to get the real world values and see what it is.
Did you try it?
I unfortunately was sick and I was on medication at the time, and I was afraid of taking strange substances with the medication and how it would interact.
Do you have a picture?
I do have a picture, and so I will show the picture, but I don't want to go through my computer with it connected. We were doing a Skype meeting yesterday with my summer research students with a colleague who was helping us, and the student didn't realize that her computer was projecting as she was going through her file with all of her passwords. So you really, take it! And just trying to get her in the habit of, you always disable, you always hit video mute before you start searching for things on your computer. And that's why I'm not going to go right now and open up an Explorer and start looking at things.
These examples are great, the projects are superb. What I mean, you spent a lot of time to discuss guts of ISA algorithm.
Right.
It was published in 1977.
Right.
But for more than 15 years, it was not realized. due to restrictions of computing systems at
Right.
that time. So this is my point. How you illustrate classical concepts like ISA algorithm on equipment that is available to students.
Are you talking about available to students now or available when it came out?
No, you teach.
I teach
don't know,
now.
for
Okay, so
last, 8 years, I don't know how.
okay, so
Reasonable.
yeah, so here is a mathematical file that I wrote that allows me to implement RSA in real time on a laptop. And so I will make this, so I will make this file available. You know, for other things like the Caesar cipher, there's no need to really make this available. You can go online and do it without too much trouble. But the difficulty here is how do you implement the Euclidean algorithm in an efficient way? Because you need to find that E and the D. And so I agree with you completely that students need to see what are the issues with implementing. And they need to learn how to code well and how to debug code. And you're forcing them to actually write stuff to do this is tremendously valuable. Yep.
How do you motivate the students, similar question, to find the primes, to help them? I mean, I would imagine that's a big part of this program is getting your primes.
Right. Well, yes and no. So let me see. So Mathematica is a beautiful function called next prime. And so now I can do this, and that's a cheat. And so the question is, do I want to have them encode Fermat's little theorem? Or do I want to say, you know, look, there's so many different things we can do. Let's focus on the difficulties of implementing fast multiplication and finding the E and the D, and let's not really worry too much about finding the primes, and we'll just use this. Then the question is, well, how well does this work? And so let's take a number, 10 to the 100 plus that. That works pretty quickly. 10 to the 400 plus that. That works pretty quickly. 10 to the 4,000. Oops. Now it's pausing a little bit. Okay. So, there is a mortality here. And so, okay, 10 to the 4,000, this is no longer working instantaneously. And, we can let this run for a little bit as we're talking about other things. But at 10 to the 400, it was working essentially instantaneously. And so it's an interesting question as to how many things do you want to have them do versus what are you willing to have them just pull in. If they pull everything in, then they're doing nothing. But there is a value in learning how to use the libraries that are out there. And different environments have different things. So given that this is having trouble now, one of the things that's hard is you can't really tell where is it in the calculation. How close is it? If I'm exactly, if I abort right now, is it about to turn out the answer? So what you can do is you can take a slew. Mathematica has a nice function. Just break this. So let's go to maybe 700. After 700 was still almost instantaneous. 900. All right. Let's try 1200. Right, so 1200 was a little bit of a pause. So what I can do is I can do timing. And if I run that, this number here tells me it took 0.79 seconds. What I'll do now is I'll add plus random integer, I think 10 to the 56. I think should give me, oops, did it not work? Random integer. Okay, yeah, so that should be working. Okay, good. So now it took 1.625, previously took 0.5 seconds. So there's going to be a little bit of a variation depending on where you are and how lucky you are. So what you could do is you can have some kind of random integer and run this maybe 1,000 times and then do an average value for starting at around 10 to the 1,200. Then do it again at maybe 10 to the 1,300, then 10 to the 1,400. Gather a bunch of data points. And this is now a great way to talk to students about statistics. We want to try to figure out how long will it take us to get to 10 to the 4,000 or 10 to the 40,000. Do we have a hope of having this run? Well, we do a bunch of smaller simulations here. This time it was about 2.89, or 2.859. And now you can use this to start talking about statistics. But you can see that there's a tremendous variation from 2.5 seconds to half a second.
When RSA was first developed, was the technology, it wasn't this quick, but it was quick enough that they could actually make use of that? Or was it theoretical back in the 70s?
It was very time consuming. It was not real time. You couldn't send a message real time, but you could generate a message and then send a message later. Like it was, you couldn't do online banking, but I could encrypt something, send a message to someone, and email them the message, which is what drug dealers used in the 70s. They would encrypt the message, send it, and then not that person. No, your experience is from the 80s, right?
My question is a little bit outside of the second part. It's about blockchain and cryptocurrency. And are they using RSA?
I don't know what they're using for blockchain. Does anybody? Oh, no, Max, the drug dealers, one of the drug dealers, one of the programmers sold out the drug dealers to the FBI. And that's when they were able to bring down a couple of the cartels. The FBI outdid, they got this programmer cheap. And he thought he was being underpaid and sold him out. It was, he programmed it in RSA. But again, it's not a real-time communication. Like now you can encrypt phone calls from RSA. Right. Back then you couldn't. It was emails. So you put your emails, the data, the records, all the sales records, things like that. When things were being shipped and where they were going, and sold out their encryption.
So the cartels were using their wealth not only to buy weaponry, but also to buy technology. To make use.
Yes.
In its infancy.
Yeah. So to just get a sense of real time, so here is something I've made to just implement RSA. So I'm not going to show the earliest stuff where I've introduced a lot of the functions. So I'm going to just compile this line, and then the first line that I'm going to run is create RSA. And it's going to print out a couple of outputs. It's going to print out here is my value for E. Here's ED mod P minus 1, Q minus 1 is 1. Here's my N. Just see. Here is what P is, here's what Q is, here's what D is. Now, obviously, if you were going to implement RSA, you would not print out what P, Q, and D are. This is just for the purposes of having conversations. It took no time for it to generate stuff like this. This compiled, instantaneously on my laptop. And I'm looking at numbers with the primes of size 200. So, the compilation time was, less than a fifth of a second. So now that I have that, if I want to send a message, here's some code to send a message. I'm going to just randomly choose a message between 1 and the public N. So here is my message, and here's the encrypted message. And again, it took no time to encrypt the message. To decrypt the message, I will run this, and again, essentially almost immediately it decrypts. So to implement it now, at the level of 200 digit primes is not a problem at all.
But you cannot list all 200 digit primes.
No.
And let's just try all combinations.
Well, there's about 10 to the 90 roughly doohickey thingamabobbjigs in the universe. So if you wanted to list, there's around 10 to the 198 primes up to 10 to the 200. So if each doohickey thingamabobbjig was one of your primes, you wouldn't have enough to do even square root. So there's no way to do a direct enumeration. There's no way to do any of these brute force approaches. It has to be something else.
One thing that was mentioned earlier is that Steve and Jim wrote a high school cryptography module that's available free of charge from COMAP as part of the VCTAL collection. So if you're working with high school students or you're working with undergraduates that may not be better than high school students, you may want to get a hold of a copy of that, because the key piece is it has a lot more problems to try, to have the students try to work on in the midst of everything else. This book has everything at the end of the chapters, and so it's more designed for a higher level course. So.
And we also wrote a streaming information one on error detection and error correction.
Right.
Which is going to be the last thing I'll be talking about.
Well, even, the video streaming one was really that.
Right.
So there's, if you just go into the COMAP website, type in VCTAL in capital letters, it'll bring up the whole set of modules, of which there are many. And it's those modules that we combine to create a professional development course for high school teachers in computational thinking. So we have a unit on cryptography. We have a unit on streaming.
Right.
We have a tough unit on recurrences. If you'd had to pick the one that would be the hardest, it probably, those who teach computer science would probably agree that teaching recurrences is the hardest you can do. But.
I think for recurrences, a lot of it's the freedom of what you can look at. The other ones are much more focused.
But, on the COMAP website, all you have to do is sign up, and they will send you electronic files of all the modules. And there's also a set of 20 modules in biomath. So if we were doing anything at the interface of biology and mathematics,